Okay, hi guys. I wanted to talk quickly about the text file collector that I think is often ignored feature of the Windows and Linux-based collector. So basically, anything that looks like a proper Prometheus metric format ending in a file with .prom in a write folder would get collected when scraped. So for example, if I were to echo PromCon attendees, blah, 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 250 into that folder by default in Debian, then this will be exported. Right now you can see also that export the time of the modification of the file. So that could be really interesting for alerting. So sometimes you could need it because you don't want to bother to open a new port across your security groups or firewalls or IP tables. You need to update Prometheus configuration as well, and extra. Or you want to have new exporter developed, so you have to copy paste some boilerplate and get started. So you could do server health check really quickly. You have Ghost. That's really useful for that, but you can also look into your application health check if it's like legacy or something. With a simple curl, you could output the HTTP code. It's not really perfect, but it works and it gets picked up quickly. You can also have metrics for exotic RAID systems, LVM, other devices, maybe Modbus, as we've seen. And you can also track job progresses, like a long rsync or something, like what's the last time there was a synchronization, how many files, what's the size. And if you don't have any news from your job for some time, you can look up the TextFile end time metric and alert on that. It's sometimes easier for those systems to write a file than to make a HTTP request to a push gateway. It depends. There's also something that's why I wanted to speak about this is the case of multi-threaded daemons, and I think we have a talk tomorrow afternoon about this. For example, FluentBit, if you need to have several workers processing files and stuff like that, it will just open a new port where you have the Prometheus metrics. So if it's dynamic, you will have to reconfigure Prometheus to scrap the number of workers. So you could do something like curling all the metrics and put it in a file, put some regex so you can append the PID or the port number, and then you have all the metrics in some place. You could also update FluentBit and add that feature. That's something we tried, but I'm not really a good expert in C code, but it's really easy to do. Sometimes, like I said, a shell script, or it could be Python, or maybe even a Go script, but then just what's an exporter. They're easy to deploy. For example, you can just put all of them in the cron folder, and then they get executed periodically. And it gets the result done in a few minutes. And also, and it's something, that's why I really like the Prometheus community, there's already a few scripts that have been contributed. So for example, for APT, you could have the unintended upgrades count, something like that, or the NVMe metrics of your systems. And that's pretty all I wanted to talk about. It's really a feature that needs to be used more, I think. Thank you.
Okay, thank you, Adrien. Okay, so my talk already gives it away a little bit, but there's something that I've been thinking about for quite a while, and if you maybe were at KubeCon earlier this year, you may have already heard about this, but here's the scenario, and many of us have probably noticed or experienced this before. So let's say you get some sort of an alert, and this is actually something that we have in our infrastructure, for example. If there's something that actually has been crash looping for quite some time in our infrastructure, we get a warning alert. We don't get woken up about this necessarily if it doesn't violate our SLA, but we do get notified about this. So what do we do when we do this? We look at actually the data that tells us that this pod is, in this particular instance, it's a pod on Kubernetes. So we look at the data and it tells us it was killed. And what do we do then? We look at the memory usage of this particular workload. And when our workload is killed, that is when it's allocating so much memory that it wants to allocate more than the machine, for example, has available or that is available to this process, it gets killed by the Linux kernel. So this is a very typical picture that you'll see from an killed process. And wouldn't it be nice if we knew exactly the profile right before this program was right? That's usually when there's a memory leak or something. That's the most interesting data point that we want to look at. But this process has already died, so we can't profile it anymore. So the problem, the solution to this problem isn't particularly new. Google has written about this for a couple of years already, and the concept is called continuous profiling. So it's actually quite simple. Just like with metrics, that we collect metrics over time, we collect profiles over time. And as it happens, the Go runtime, for example, and there are many other integrations for other languages out there, actually exposes an HTTP server, much like a Prometheus endpoint, but for profiles. And this is the pprof format that it exposes. So what do we do typically when we look at these profiles over time, right? We look at one profile after the other, and we look at where has this profile changed over time. And we kind of look at this and identify this with our human brain, but wouldn't it be nice if we could more automatically do this? So basically what I've already built is a tool called Conprof. It's very imaginative of myself to call it Conprof because like continuous profiling, right? But I want to show you a really quick example from our infrastructure. So we have a process that actually did here and then was respawned here. As it happens, this is actually Conprof itself. And so wouldn't it be interesting to continuously profile Conprof to find a memory leak in Conprof, right? So right here, we see something this happened yesterday evening or yesterday night. And we don't have a profile of this process, or this process isn't running anymore, but because we have Conprof, we have continuously profiled it. So let's look at a couple of these profiles over time. So we've got this one, and we've got this one, for example. So I already did the hard work of choosing a time range roughly where this process was still available. And we can see that the majority of this process keeps being allocated by this particular part of the program. So now I know that this is actually where I should be looking first when I troubleshoot my application and want to fix it. So that's basically the functionality of Conprof that exists today. And you can check it out today for all of this functionality that you just seen. But actually, there's something, because I still have roughly a minute of time that I want to talk to you about, which I think is super cool. And if you want to help me implement this, then please approach me afterwards, or just go for it and implement and send me a PR. So Prometheus has the remote read functionality where you could convert any kind of data into time series data and then query it and visualize it with Prometheus, right? So we could convert multiple profiles over time, and as it happens, samples in a pprof profile are also identified by a key value label pair. So we can have the exact same data model over time, and if there is any sample that is growing over time, then we've just identified our memory leak automatically. So if you want to help me implement that, please approach me. Thank you.
Hi all, I'm Sanjay. I'm from IBM, and I have been working with one of the largest telecom provider in India for IBM. So basically, I was part of application modernization team there. And after the application modernization was done, we were using Prometheus for basically monitoring the data for all the microservices. So today I will be sharing my experience that we have gone through and how we overcome the challenges that we got in monitoring the microservices. So after all the application was developed, basically all the monolithic applications got converted to microservices. The challenge that we faced in monitoring those microservices was, so as you can see, all the operations team before in the staging environment, when we delivered it to them, they told us that, okay, this is monolithic applications monitoring was easier because we have new dimensions in having microservices. So basically, we were getting issues like horizontal pod auto scaling not working, and disk available to a specific application is at its full capacity. Some nodes in clusters are oversubscribed, and network bottleneck caused by dropped packets. So basically, the issues that we were getting in the Prometheus at that point of time, we used that data to basically replan our infrastructure based on the data that we received. So basically, the data that we received based on that we basically replan our infrastructure, CPU, RAM, network planning, deployment, everything. And after this is done, still our life was not easier. So basically, the day-to-day scenario that we were seeing is alert manager was sending alerts to for unhealthy services, and there were some fake alerts. So the admin team has to identify which was the ticket to be opened, and the biggest challenge was the ticket that they need to open. They need to first make sure that it is not for admin, it is not for it is not a fake alert, and also he need to basically go manually and open the ticket, and also he need to make sure that he don't open the duplicate tickets. So how we overcome it? So basically, first of all, so the fake alerts that we were getting, we basically overcome those things by using grouping, inhibition, and silences. So in grouping, what we define, basically what all alerts are similar. So basically, those alerts will go in a group. Only one ticket will be opened for that. Only one alert will be generated basically, and the inhibition. Basically, if an alert is being opened, so the same alert should not be open for a certain period of time, and then silences. Basically, those alerts that we suppose the node is under maintenance and we know that the alert will come. So basically, we don't send those alert manager don't send this to the intended target like alert the webhook or emails. So after this was done, the next challenge that we were facing was when there is any issue, basically operations team will need to go and manually check what are the alerts are, and they need to open the ticket. So basically, as we know, in case of microservices, and it is very new for all the team. So basically, if they take time to open the ticket, like they take around 2 to 3 minutes or 5 minutes to 10 minutes, when we want that the team which has developed the microservice should be involved right after the issue has come. So we wanted that the ticketing system should be integrated with the basically the alert should directly go to the ticketing system. But the challenge was it is not out of the box supported for us. So we defined one more component between a ticketing system and alert manager, that was ticketing system provider. So what it does basically, it basically collects all the data that comes, and then after collecting the data, it basically opens basically the format the data comes for the ticketing system provider. It converts it to the format that ticketing system understands. Like ServiceNow has a standard format in which if data goes, then only they open the ticket. So that part is done by ticketing system provider. And also but still the challenge was there are 10 to 20 teams in the internal system. So yeah, so in the system, so basically how we will make sure that the ticketing system should open the ticket to the particular team. So for that, in the microservices development, we have defined such a way that the matrices should have the organization and team name. Okay, so the team name with which the ticket will be opened, and the team will immediately start working on the issues. So lastly, as you can see there, the notification received by the webhook receiver is this. And then for ticketing system provider, the code that we have written so that it converts it to the format the ticketing system understands. And this is it.
Thank you very much, Sanjay.
Yeah, my name is Burkhard Noltensmeier. I'm the founder and CEO of Tovena. We are working in the northern part of Germany and delivering services with OpenStack and Kubernetes to our customers. And we got in talk with a wind turbine operator in our region, Westfalen-Wind, and they operate these huge wind turbines. They are 120 meters in height and have a power amount of 2 or 3 megawatts. And we got in talk to them, and they already have some kind of SCADA system which have this data in place. And they've got an ancient dialect, a SOAP dialect, OPC XMLDA. And fortunately, we find a library in the internet with 0.1, the last release from 2006, I think. So we managed to write an exporter for that, and you can see what we get out of this operator, like the middle wind speed, the yaw, the axis of the nacelle, and the power of the plants. And this is what we export from the wind turbines. and yeah, some other metrics like operating hours, temperature of the nacelle, and yeah, power. So, and this is the architecture that we can come up with. So we get the data from the left, from the Enercon system, and then we have got a small metrics extractor, and then we pull it into a Prometheus database, and yeah, then we put some more effort into have some dashboards and visualizing the data, which I will show now. So yeah, Grafana, as you may know, and Jupyter Notebook, and I will switch now and try if it's working. So, and yeah, oh, thank you very much. Yeah, yeah, here we have got a dashboard. So we did a dashboard in Jupyter Notebook, and this is the Kennlinie, don't know the English word. So it has got the kilowatts of the wind turbine and the wind speed on the x-axis, and you might see here the Python code, and in the middle there is a Prometheus query here that we get the regions, the plans, and then we can populate the dashboard directly from Prometheus. So I can select here a plant, and then it will fetch the data and calculate. So it will take a second or two. Hopefully it's working well. Okay, usually it does. And it will fetch the data. Now it fetches some data. As you see here, sometimes the wind turbines are capped to a certain amount. So this wind turbine was kept there at 1 megawatt. And yeah, this comes from the grid operator. Sometimes the wind speed is so high, the power turbines are kept from the grid operator because the grid is not able to consumption all the power. So here I have the raw data in Prometheus, and what we may do is we can get the angle of attack of the wind turbine. Unfortunately, the wind turbines can turn several times, so we have got 3 bands 360 degrees apart, but we can do some simple operations and do a modulo, and then we can have all these bands joined together. So unfortunately, mistake. So we have got now 1 band. So this is what Prometheus enables us to have yeah, a better sight on the physical data. And on this slide, yeah, you can see the average wind turbine, average wind speed, which we consolidate by wind park. So there are 4 wind parks here, and you can see the consolidated speed. On the top here, you can see the power capping from the grid operator. So every time there's a lot of wind energy, a lot of wind, the grid operator caps the power limit. So it's kind of not so good. So the grids really have to be extended in Germany to take more advantage of these renewable energy. Yeah, so we also managed to build a Grafana dashboard. Here you can see the consolidated power of the wind park. So it's got 25 megawatts here. This company operates 100 wind turbines, so it's a lot of power that can be potentially generated. So you can run several data centers from that. And I've got 1 video from top of the wind turbine that might be interesting. So the 110 meters, it's a little bit scary, so I'm looking a little bit concerned there. But so it's a huge operation. Yeah, thank you very much.
So first of all, big thanks. This is not part of the talk yet, but big thanks to the video people. They just brought a small screen backstage to test the video and doing an overall great job. So thank you. All right, so I want to talk to you about SLOs. And first of all, I'm Matthias. I work at Red Hat maintaining some projects like the Prometheus operator, kubeprometheus, and became a recent Thanos team member for maintaining kubethanos. So SLOs. SLOs are known from the SRE book or many other places, and they specify a target level for reliability for a service, and they yeah, make it happen so that you can make
data-driven decisions about the reliability of your system, so they're quite essential. SLOs, however, are actually built on top of SLIs, and you can think of them, if we're talking about RED, for example, of requests, errors, and duration. And in Prometheus terms, this might be something like this, where we have a rate of the HTTP requests total in 5 minutes. And then building on top of that again, we come back to SLOs. So you might want to have an SLO where you want to be alerted if the error rate is above 1%. We could call this kind of like a service level alert in Prometheus terms as well. Yeah, so we can be smart because we have an SLO, we also have an error budget, and we can be smart about alerting on our services SLOs. And there's something called a multi-burn rate alert in the SRE book. And we actually combine multiple 5-minute and 60-minute alerts in this case to come up with something clever to not overlook low error rates as well. And if anything from PromCon you want to take home, I really encourage everyone to put SLOs in place so you can actually talk to people about the reliability of your service and have data on that. So yeah, let's keep moving forward and look at how you can actually make use of this in your production system. So we want to implement this multi-burn error rate, and we need some PromQL. And as you can see, we have 1 hour and 5 hours in here. And these recording rules are actually based on something, some other recording rules again. And these are yeah, just one of the recording rules. So this is the 5-minute recording rule to get the ratio of 500 errors in your system. And we need these 4 times, because 5 minutes, 30 minutes, 1 hour, 3 hours, and yada, yada, yada. There are plenty of more. And these are actually built on yet another set of alerting recording rules to group HTTP requests into multiple status groups, so 200s, 300s, 400s, 500s. So there's a lot of repetition. So as many of you heard previously today before, we have JSONnet. So there's a templating language for data templating, and we pretty much use it all across the board to template Kubernetes and Prometheus things. And now we can also template our SLOs with this. Yeah, I actually came up with a library, a helper library in JSONnet that allows you to generate alerts, rules, and dashboards. And I'm here to talk about this. So this is basically just a small object you define, and everything else will be generated from that. Here's a demo of that. Where's my window? All right, cool. So you can see on the left-hand side, you can see the actual object, as I said previously, and here's the generated YAML, which is quite repetitive, as I said. And we can generate this if I'm able to tweak something. We can just regenerate everything, put in different selectors, and have different SLOs. So we can also just change the error budget. Everything will be updated. How do I actually continue with this? Great. My notes are gone, but that's not too different. Yep. So plenty of people don't like JSONnet. Maybe, I don't know, you should. I know these technologies. You can, or I thought, let's use these technologies to build something. So yet another demo. And here's a web interface to generate the YAML files. So you can just put in the availability, the metric, put in some selectors that you might want to have, and generate that thing. Copy it to your entire Prometheus and use it.
Oh, thank you very much.
So welcome. I am Matthias at Red Hat. I'm a senior software engineer, and I'm working for the OpenStack group there. So this is a bit different for the main audience here. So the idea was to get metrics from OpenStack clusters, and you just see one cluster or one compute node on the left-hand side, but it could be 1 or 10 or 1,000 or however. And the idea is to use, for example, collect-D or the traditional telemetry in OpenStack to collect data and to send it over to a microservice application called the Service Assurance Framework. And it uses a AMQ1 bus, which has major benefits. I'm going to get into that. And also a component we are calling the Smart Gateway. It's an awesome name. So it both provides metrics and also logs or events to an endpoint. In this case here, we are using the endpoint for metrics to send the data to Prometheus. The AMQ bus is smart enough to provide some high availability, and just in case some core node goes down, it gets replaced by other routers. That's the basic takeaway you need here. And another benefit of this is it also works on edge nodes, which is the next big thing, or you could replace edge by 5G or whatever. It's just another buzzword. But in any case, you could just send the data through your network, which is connected from remote computes to your central data center, and you'll get the metrics there. So what has it to do with OpenStack? In cloud environments, you would also want something like autoscaling. And since the core components in OpenStack are a bit slow or a bit a pain in the ass, the idea was to rip off like AODH or Gnocchi and replace it with Prometheus and Alert Manager. So the way these works is you define a software stack, like a stack of VMs or whatever, in a template language named Heat or Heat autoscaling templates. You define an alarm from when some more servers need to be scaled up or scaled down. And you check that alarm and fire an event if that happens. So that basically translates to Prometheus and Alert Manager as well. But Heat, AODH, and Gnocchi, and so on, they are all multi-tenant. And this is nothing known in Prometheus and Alert Manager. So that is becomes a pain as well. So the other takeaway here is, even if you could solve the multi-tenant issue, you would also add another technology stack like OpenShift or Kubernetes just to run OpenStack, and that's nothing you really want to go since the autoscaling is a basic cloud functionality. It should be provided by the cloud or by the infrastructure itself. So Service Assurance Framework is still a useful component for collecting metrics and events from your OpenStack infrastructure, and it is designed for consuming loads of data, like 100 metrics per second from 5,000 nodes or so. But the autoscaling use case is nothing this stack should solve. Thank you.
Thank you.
All right. Hi. So I'm Julius. You probably know me already from earlier today. This is improvised. I just wanted to talk a bit about the new UI. So this is, the current UI we have in Prometheus. It's neither particularly great nor particularly bad. It kind of does its job, pretty simple. We do want to keep it simple, but we always had the wish to, add some kind of state-of-the-art features to it, like auto-completion, syntax highlighting, just have a bit more of a modern framework to actually build on, because so far it's all been based on, basically, most of it at least, on this one huge jQuery-based JavaScript file, which I started in 2012, and then people just added cruft onto it. And so we had various discussions around like building it properly in a new framework. for various reasons, they never really ended up anywhere. But in February, I had some time, and I just, it's like I had motivation. I was like, okay, I'm going to teach myself React, and I'm going to teach myself TypeScript. I'm not really a front-end person, but ended up kind of doing that. Ended up building a new graphing and like console table UI in React and TypeScript. Loved it, but didn't really get to actually integrate it until like 3 weeks ago, which was kind of hairy to do in Prometheus. It's this huge PR about like 13,000 lines added, and quite tough in some ways. But the great thing is, once I managed to do that, I tweeted that. This was 3 weeks ago, and since then, my God, I think the new UI has gotten like way more contributions than the old UI has gotten in the whole many years before that. So like all these pull requests, I just searched for UI. It's a whole page plus like half a page more, like from 5 or 6 different people who all flocked in and were like helping to implement various parts of it. Some are in the audience here. This is still the old UI, but there's in the release that's going to be released now. We're like roughly today, right, Chris? Release. Oh yeah, there you go. The release candidate's out today. The main UI is still the old one. There's a link to the new experimental UI. If you click it, you get to the experimental one, which has, it has the graphing parts and everything. Let's see, am I on 100% zoom? Yeah. Well, this. And, some of the sub pages, by the way, the whole nav and all the other pages, like they were added by contributors now. It's all a single page app now. It's based on APIs and just fetching the data from APIs. And yeah, the graph view, right now it's still pretty much what the old UI was. It's probably also going to stay roughly along those lines, maybe a bit prettier here and there. There's a time picker and all that you're used to. And, but now you got this like very beautiful rotating spinner on the left, which, okay, it loads too fast. But yeah. And maybe like slightly more beautiful. And of course, it's just the beginning. There's already plans, like there's an Internet Red Hat working on a language server protocol implementation on the Prometheus server side, which could then on the UI side help us do things like proper auto-completion, syntax highlighting. I think we should probably keep them very lightweight and maybe even optional, because autocomplete gone wrong can really be frustrating. But yeah, that's kind of the way where we want to go, and maybe do some smaller other features like, type hints here and there and things like that. But we don't want to be a competitor with Grafana, of course. Like, it's just for this ad hoc kind of exploration of data. We want to give a bit more state-of-the-art new UI. And yeah, so basically try it out, file bugs. If you see some pages that are not implemented yet, you get like this kind of under construction notice. You can go back to the classic UI. Well, this should work. Okay, yeah, maybe we should fix that. The React router doesn't do that properly yet. Actually, I think, no. Okay, yeah, that's basically it. I tagged issues related to it with the component/React UI label. Most of these are kind of being worked on already. So at the moment, there's a lot of planes in flight, but I hope it kind of settles down in the next weeks, and then we can stabilize it and give you more cool features soon. Cool, thank you.
Thank you, Julius.
Hello, everyone. I'm Cyril. I work at Grafana Labs on Loki. And today I want to talk about LogQL to give you a quick introduction. So I want to start by a quick question. I know you know Loki. So who knows about Loki? Nice. Who is using Loki? Nice. Who has tried Loki? Even more. Nice. Okay. So for those who don't know, Loki is a log aggregation system that we built at Grafana. It's all open source, so give it a try if you want to check it out. So what is LogQL? Obviously, LogQL is the language to query for logs on Loki. It's heavily inspired by PromQL that Jan talked today. And I actually had a lot of slides about PromQL to explain, but thank you. That's awesome. So I'm not going to have to talk about this. So it's heavily inspired by PromQL, so you don't have to learn another language. As Jan explained today, learning another language is sometimes difficult, and we want it to be distributed grep, so you can query across multiple across your workload. So in PromQL right now, when you want to select data, you have a metric name, label matches that defines your workload. So cluster, job, instances, all of this is you know about this. In LogQL, it's pretty much the same, except that we don't have a metric name because there's no metric. So we still have label matches. And if you use the same set of label with your metrics, you can also have you can switch between logs and metrics. We also added filter expression. So filter expression allows you to actually filter on the log itself. So we support the same kind of filter as PromQL has. So contain a string, does not contain, and matches regular expression. We recently added a new feature where you can count logs. So it works using range vector. So I'm not going to explain what's range vector again today. I think we had this twice. But the idea is you can have the per second rate of your logs, and also you can combine that with the filter expression, so that supports filtering on logs. So you can check, how many errors, error logs I have in a time frame. So since this outputs metrics, you can use the same aggregation as we've seen today. So the sum, min, max, top k. And we're going to do a quick demo. So let's imagine that I have a trace, right? I'm trying to figure out what's going on. You may not be able to see it, but this trace has actually 3 different services. And if I want to actually look at the logs, I'm gonna actually have too many logs. So I use the dev namespace in US Central, and there's too many logs for me currently. So that's not what I'm working on. And I want to filter only on the queries that I'm working. So for that, I can use a filter expression. Right, so I'm giving the trace ID. And now I can see only the logs related to that trace. So Grafana has a nice UI where you can see it's actually showing the matches. Sorry, last one. So this is so since the Loki is 100% compatible with the Prometheus data source API, you can use Loki as a Prometheus data source, and that's what we can see here. So it's a Loki Prometheus data source. And you probably know about this keyword in Golang, the error keyword. So I'm going to look at, in exactly, I think it's 3 hours. Yeah, 3 hours. What were the job doing errors? And yeah, that's it.
Okay. Hello, everyone again. I think those issues, I don't know, like I just joined Red Hats and I have a Fedora laptop from 2 months, so I'm learning those tricks. Hopefully it will be better. No, it's actually pretty deterministic. It was my fault. Anyway, so, okay, I want to just quickly go through, spend 5 minutes to quickly go through the RemoteWrite improvements we did this year on the Prometheus side, and particularly why it's important and what we improved. So first of all, what is RemoteWrite API? RemoteWrite is this endpoint/read that is available on the Prometheus server, and it allows you to select the series from the internal database that Prometheus is using, which is TSDB. It fetches series, matches series, and at the same time, query range does exactly the same. However, query range goes through the PromQL engine that does the evaluation and stuff. However, the important part is both RemoteWrite and the query endpoints are using exactly the same interface endpoints to the TSDB internal database. Now, what are the use cases for RemoteWrite? So it is used mainly for the integrating with other systems. So it was built mainly for the sys-service to sys-service communication. That's why it was designed from scratch in the protobuf over HTTP. And the protobuf is like one of many general serialization mechanism from Google, and actually a pretty neat one. So what this message returns, it returns you the requested series, all the series within one message with all correspondent labels and row samples. And the use cases would be, you know, the Prometheus reading from another Prometheus, maybe with different versions, or Thanos reading from Prometheus. That's a very well used kind of user of the very popular user of the remote read nowadays. And also you might have a Prometheus reading totally from different system that is totally different than the Prometheus internal database. However, expose metrics in the similar form, so PromQL can evaluate that data. So what is the problem with this approach? So first of all, yeah, during this request, you can see that the internals, we select the data from the internal database, right? And the response is a series by series, stream of series by series, right? And because everything we store are mostly compressed in chunks, so the samples are compressed in the XOR and coding format called chunks. On each iteration, we have to decode those into row samples and put into huge buffer to fill this protobuf message. So you can imagine that, you know, it takes time just to fill the request, and only after it's after all the series are done, return, we can marshal this big protobuf and compress it and send to the client. So what's the outcome? Yeah, we use excessive amount of the resources. For example, for like 8 hours, 10,000 series, both Prometheus and Thanos were using a lot of memory, mainly because it has to buffer all the raw samples on both caller and the server side. Now, what we did to improve that? We introduced a new protobuf message response, so you can use exactly the same remote read, but from Prometheus 2.13, you could ask for the streamed XOR chunks response, which gives you what? Chunks instead of raw samples. So this allows you to reuse exactly the same format Prometheus use on the storage level. Now, we also allow this message to be chunked, and chunked by whole series or portion of the series with correspondent labels and chunks. And we trim those frames into maximum of 1 megabyte. So what we can now do, we can stream we can stream directly through all the steps. We select and we grab all the series by series, and for each we frame it, compress, marshal, and send it, or marshal and compress and send it. What's the outcome? We reduced the amount of memory for the same request enormously. So where just this selection takes for Prometheus some amount of memory. However, for Thanos, it's like almost zero and a constant amount of memory because it frames, it puts the remote read API response and puts into gRPC stream and nothing more. So this also reduces latency and two more, and like the CPU time use. So anyway, the outcome of this is that you use the newest Prometheus. If you integrate with Prometheus, use the new remote read API as well. And here are the links, and one of the links is like Golang client that already have benefit of using a streamed version of the remote read.
Thank you, Bartek.
Hello, I'm Tina. I'm going to talk to you about my work in Debian for the Prometheus packages. This is the 4th time I do this talk. Probably a bore about seeing me, but well, keep on working, so I keep on reporting. And also I like this community, so. I'm a Debian contributor since 2005, became a developer in 2008. I used to work at Google. That's where I got into Bormon and then Prometheus. And for the past 6 years, I've been a freelancer. So I gave a talk about that last year. You can watch it. It's great. Be a freelancer. Don't work for companies. So a bit more about me. Probably many people here know me from before. I look different and I use a different name. I'm 42 almost, and I'm trans. And I'm very happy. Thank you. So, little show of hands. Who uses Debian or derivatives in production? Yay. Who uses my packages? My Prometheus packages? Well, a few. That's great. My work is still useful. I'm glad. Well, by Debian, the usual thing I say, we are not hip, but we're still relevant. We run on everything, on space stations, and on cell phones, and on embedded devices. Many release arches, so that means like nine architectures are released every 2 years, with like 99% of the packages. And we have like 120 derivative distributions, including Ubuntu, Mint, sorry, and others, don't remember. We provide trusted binaries that are mostly reproducible. Golang is still not reproducible because still some issues with the compiler, but we're almost there. We provide package management, so you don't need to deal with installing and uninstalling things by hand, integration, proper defaults, security support. Hopefully for Golang this time we're gonna have security support if we manage to get the Go libraries to behave a bit better. And even if the release cycle is 2 years, we do also a lot of work on backporting stuff. So during these 2 years of the release cycle, I will be keeping on updating the Prometheus packages for the already released Debian. So in Debian nowadays, in the last 2 releases, you can just do that, and you have Prometheus up and running in no time, a reconfigured to monitor yourself, and a local node exporter. Most of the packages are available in the 9 architectures. Prometheus doesn't work in 386 nowadays, but all the others work. I almost finished by porting the latest versions to Stretch, which is the release from over 2 years ago, and about to start backporting to the current release with the new versions. That's a lot of work, so it will take me a while. We still have a very small group of maintainers, so always help is welcome. This is the current status in versions. So you have what was released earlier this year is stable, and the column on the right is what I've been working the last month or 2. The ones that have asterisk is because I've loaded them today. But those are all current versions, I think. We have the client libraries also, Golang, Perl, Python, and Ruby. We have like 23 exporters. Those are maintained by different people, not only me. You can see Apache, Bind, Bird, the Black Box exporter, HA proxy, APMI was uploaded like 2 hours ago. Thanks to Daniel. Mail exporter, MongoDB, MySQL, Nginx, Node, PostgreSQL, Postfix, Postgres, Process, SNMP, SQL, SQL, Traffic Server, and Varnish. Loads. So it's a lot of work. Julius is gonna make my life a lot more difficult soon. And yeah, as I always say, it's difficult to package all this because of JavaScript and Golang. The way the things work is constant work, constant chasing behind the changes. And as I said, I still want to work on JSON.NET to provide better integration, but I have no time. Many things to worry about this year. There's the complications. Well, there's not much time to talk about that. So if you're curious, there's the link there with all the versions and current status, and there's an IRC channel. You can chat with us. And thank you very much. I'm still available for hiring, and see you next year in my next lightning talk.
Hello. Okay, cool. So just really quick, I'm going to talk about some improvements to RemoteWrite, similar to what Bartek just talked about earlier. All right. So this slide, I guess, probably isn't necessary, but the gist is that RemoteWrite will, if you configure it to, send all of your metrics somewhere else other than Prometheus. For various reasons, you might want long-term storage in some other system for a different query language, or in our case, we want it for Cortex and a different query parallelization. Really quickly, this is the Prometheus architecture. I'm pretty sure Julius made this diagram. Thank you for this. No? This is a different one? Ah, thank you. Okay, so previously, I think on the next slide, previously RemoteWrite over in this retrieval bit on the left would basically make a copy of every scraped sample and buffer it all in memory until it could successfully send it onto the RemoteWrite system. You can imagine that might not be a good idea. What happens if the remote write endpoint goes down and you continually buffer data? That buffer was a fixed size, so if that fixed size didn't happen to kill your Prometheus, you would eventually just start dropping data, which is something you don't want either. If this remote storage system is supposed to be for your long-term storage, but you don't end up with all your data there, that's not good either. So in order to fix that, the way remote write works now is it just reads the same write-ahead log that Prometheus is already generating. All of your data is scraped. The write-ahead log is written. That all that data is there until eventually something's written to long-term storage on disk. So we just tail the same write-ahead log that is already been written. There's still an internal fixed size buffer. The catch is that we don't continue to read the write-ahead log if the buffer is already full. So in theory, remote write will no longer your Prometheus. The one side effect is that when you scrape your endpoints, you get the metric name, all the possible labels, and then the value. But in the write-ahead log format, you get the labels and metric name once, and then from there on out, you just have a reference to an ID, and you have to go look up those labels. So if you've noticed, newer versions of remote write in the happy path use more memory, but in the worst case scenario, it won't crash. All right, this was the end of like 6 months of work, but there's been more going on since then. We're still working on the sharding bits, but thanks to Chris, where's Chris? It mostly works now, other than when you restart Prometheus, it doesn't necessarily catch up very well, which is unfortunate, but I'm working on that. If you have other questions about remote write, find either one of us, because we're working on it. That's it. Thank you.
Thank you, Callum.
Hello, everyone. I'm Tom. I've been an intern at Grafana Labs during the summer, in which I've worked at Tonka, which is basically, does somebody around here know KSonnet? Okay, for everyone, when Heptio was acquired by VMware, KSonnet was abandoned, but we depended internally on it. So we decided to basically rebuild it. And that's the result of 6 months work on it, 6 weeks work on it, is Tonka, which is effectively the same thing, just in simpler. So the main problem we're about to solve is when you're in the world of Kubernetes, you usually deploy things using search manifests, but these are environment specific. So you have things like a namespace hard-coded or some ingress annotation, or especially a host name. But you might want to reuse these pieces of code in other environments like prod or dev or whatever. But the Kubernetes YAML tooling does not really help you there. But as some other people mentioned today as well, there's JSONnet, which I need to go to my laptop for this. Basically, it's JSON, but with some additional things like it supports variables. You can see here the local is a variable and it's used in JSON. It supports functions. It especially supports imports. And one of the most interesting features is deep merging. So if you have one dict, you can merge another one on it without overwriting, while only overwriting what is specified in the other one and leaving the rest intact. What does it help us? Well, it's basically the same as with KSonnet. We can modularize our whole Kubernetes config. We can do a high level of code reuse, and Tonka still supports the main workflow of KSonnet. You write your JSONnet, you show it as YAML, you diff it to the Kubernetes cluster, you apply it to the cluster once you're happy. You have environments, so you have high-level abstracted code outside, and only what's specific to a single environment is put into another JSONnet file. It's rendered. You can use your own libraries in the lib folder using JSONnet bundler from some folks about Red Hat. You can use it to pull in other libraries like Graphonet, what has been already mentioned. But we simplified it a little bit. We removed some concepts that we didn't feel were right. And all of the package management and registry is handed over to JSONnet bundle, which leaves you with JSONnet and environments. So comparison with the original KSONnet. On the one hand, there's JSONnet, what we want to use. And there's Kubernetes or kubectl, where we want to get that. And Tanka is really just a small thing in between that bridges these two tools and improves the user experience. So what we have added, some new cool things, is the first one is context discovery. So Tanka really makes sure that you at any chance never will be able to apply the wrong config to the wrong cluster. So you won't apply the dev config to the prod cluster. It will warn you, and you will hopefully see it in the big message at the bottom. We enhance the diff. So when you use KSONnet diff, you basically got this, which is not that helpful at all. Tanka uses nice coloring. It uses actual output from the diff Unix utility. And at least personally, I feel it makes it really much simpler. And of course, kubectl supported, and we use it, so it's server-side diff. You don't have any annotations mess or whatever. And for all Kubernetes versions below 1.13, we use subset diff, which is not that nice, but it at least works. Another nice thing, we added tab completion to the CLI. So if you tk diff some environment, it just suggests all the environments you can use, which is real handy because these names are long and you really don't want to type them. Another thing, targets, which is a pretty cool thing. It allows you to do stage rollout. So if you want to be able to just like install a part of it before all of it, you can specify which one. The last thing is static analysis. We have a bot build of a GitHub. If you change some JSONnet library, you can tell which of your clusters is affected by it. So for the future, the first part, it was an internal presentation before. We have already done that. It's live. It's on GitHub. It's on github.com/Tanka. What I'm currently working on is adding HashiCorp Vault secret support so that you can pull secrets directly from Vault. And another thing is that we will add support for deleting what you've removed from your JSONnet config. So you delete something there, and it will be removed from your cluster as well. So things we could work on in the future would be compiler optimizations and tighter integration with kubectl so that you can just use kubectl apply-f main.jsonnet. Thank you.